Thank you for the introduction, and I'm Yifei Huang. Today I'll be talking about explainable program synthesis. So the program synthesis problem, we're asking the users to provide their intent in the form of high-level specifications. The specification can take various forms. It can either be some input-output examples, or some logical formulas, or some demonstration. And submitting the specification to the synthesizer is responsible to generate some function f that is guaranteed to be correct. And over the last 15 years, there's been a lot of work in this field. People have proposed many sophisticated algorithms like probabilistic enumeration, conflict-driven learning, building libraries, and etc. And people have also built a lot of exciting applications using this algorithm, like synthesizing compilers, network paralysis, robot controls, and all different kinds of end-user programming. So all these program synthesis techniques or applications, we have one big hope. That is, we want to allow the programmers to more freely express their intent. But despite having a lot of this good synthesizer, it seems that no one is really using it. No one really wants to use the synthesized code in their real working environment. So what is happening over here? So let's take a look at this example from a very recent program synthesizer by Alice. So in this example, we are trying to synthesize a lambda formula that is sorting a list of integers. So as you can see, the specification are given as an input-output example in the upper right corner, and this is the final result. Notice that to accomplish the final result, the synthesizer also comes up with a lot of intermediate routine. So the blown-up version of the implementation is actually very complicated and very hard to understand. And even in the paper itself, the author has to provide useful names for each of these individual routines to really convince the reader that the function itself is indeed correct. So this raises the central question of this paper. How do we help the programmers understand the synthesized implementation better? Well, let's just take a deeper look at the previous example. Say the user wants to understand the function C13 over here. So one approach to do that is like, what about we just put the input and print the input-output of this function? They just insert two statements over here, and we pass one of the I/O example from the global function f. And then we got this for tuple over here. And by staring at it, we might say, oh, okay, so it's very likely that C13 is calculating the maximum element of this L. L indeed is. So question solved. No, exactly. This might also work for this case, but let's take a look at the next example. So here is also a specific synthesis problem that we're taking a list of I/O examples that they're string in this case, and we submit this specification to a very famous scikit solver, EU solver, and we obtain this implementation. We know that from the theory of the synthesizer, the synthesized program is guaranteed to be correct. But if we submit this program as well as the specification to another SMT solver, CVC5, it actually rejects it. So how do we diagnose this problem? So remember in the previous example, we're using print statement. The print statement is exactly answering the question like, what is each individual expression is doing in this program? But it's really not that straightforward to conclude why this program is wrong or really localize a faulty location of this program. So a more smart question would be, what should this sub-expression do in this case? Well, assume that we have an oracle in this case and give us an answer to this question. So actually, surprisingly, the oracle says nothing can be done in this case. What does it mean? It means that no matter what kind of expression you replace in this blue box, the function is wrong. So there's no fix in this case. So actually, the real place you need to look at is the later part. And so then further investigation revealed that it's actually this yellow box of subster has a discrepancy in the semantics in both CVC5 and EU solver. So we'll see by asking a smarter question, we'll be able to solve the problem or to understand the problem deeper. So with this question, it motivates our main contribution to this paper. That is the concept of subspecification, which I will refer to subspec for shorter. So to define or understand the definition of subspec, we will need some implementation f that is already satisfying the subspecification phi, and some specific location h at the function f. And there's at a location h, there's a subtree g over there in the AST. And one thing we can do over here is that we can replace whatever sub-expression at g with all different kind of legal expression over here. And by doing that, we get a family of function f. Well, some of them satisfy the original specification, some of them are not. So the definition or the concept of subspecification is really trying to capture all the possible alternation you can put at a certain location of a function f. So let's just take a look at a very concrete example of the subspec. Let's just revisit the previous example. In this case, we observe that the input-output of C13 in this case is this 4 triple. And surprisingly, the conjunction of these four examples are actually the subspec of C13 in this case. But is it always the case? Not necessarily. Let's take a look at a logical formula. And this is a logical formula given, and we have some synthesizer to give this result. And if we want to understand what kind of alternation can be put as if conditions over here, with the help of subspec, it actually tells us every asymmetric function can be put over here. So possible alternative implementation is actually just the negation of the original functions. So from this example, we can see that it's not just about input-output examples. Input-output example is not always the subspec. And the subspec itself is actually well-defined in all the fields. It's no matter in logical formulas or I/O examples. And it actually provides more information than print, because in print, you will never be able to tell what kind of alternation you can do over here. So let's take a look at the one last example over here. This is one of the specifications drawn from the Cycles Benchmark 2018. As you can see, it's a quite complicated example. And the implementation itself is rather simple. And if we calculate the subspec for the 2 locations over here, you can see it's actually surprisingly simple. And actually it tells you there is nothing really too much you can do in this program. So one of the few possible alternate implementation is just to replace the else branch with 2. So in this case, we'll see that even despite the original specification is very complicated, the resulting subspec itself can be very simple. And with this simple subspec, it also can tells you how you can do the alternation of the original implementation. Okay, so now we have motivated concept, and for the rest of the talk, I'm going to focus on how this concept can help users and how we can really obtain the subspec of each program. So we conduct a user study, which we have recruit 20 PhD students as our participant. They are coming from different fields, and we group them into different groups, and we conduct the repeated measure setup. So all the participants in different groups are asked to answer some questions. Across the group, some of them has the access to the subspec, and some of them does not. So the question of the task is something like this. The user are given a specification fee and some synthesized program. The synthesized program is not guaranteed to be correct, but they will be noticed if they're not correct. So we ask a question like, for example, can you name a function g that is a part of a function f? And can you replace g with some other g prime? And what does g do in f? And or some question like, how does f satisfy the specification fee? And also, in the case that f itself is buggy, can you really fix f? And we have a UI in this user study that the user can hover the mouse over the implementation. And when the mouse is hovered over each part, the corresponding subspec will be displayed over there. And so here's the user study. Here, as you can see, there's 3 types of questions we have over here. One is providing alternative implementation. One is to comprehend each part of the implementation itself. And the last part is about debugging. As you can see, this is the result for the scores of the participants that doesn't have the help of the subspec. It's actually pretty low, especially for a question like, why does f satisfy phi, the one that really requires your understanding. And with the help of a subspec, it's actually, we can see a significant improve in the accuracy of their response. To summarize, the subspec itself actually improves the response accuracy by 91%. So lastly, we're now shown that this concept itself is useful, but how do we get it? Well, actually, we developed a 2-stage algorithm. So in this paper, we have proved that actually, for most of the cases, it is very straightforward to construct the subspec. But the drawback of this straightforwardness is actually the subspec itself can be very complicated. So we have subsequently submit the first stage to the iterative simplification process. So in this process, we're using synthesizer itself to synthesize a simpler specification that is equivalent to the original one. In other words, we're trying to explain the program synthesizer using the program synthesizer using the synthesizer itself. So here's the effectiveness of the algorithm. So you can see the y-axis over here is a compression ratio of the second phases. So actually, the optimize is the final output, and the last one is the seed, that is the subspec we get in the first step, that is the straightforward construction. So you can, as you can see, for the Cycles task, 2/3 of the examples can achieve a compression rate of about 80%. And even for stream coder, which we don't have a very good, which the simplification algorithm cannot file completely, we still can achieve a for 90% of stream coder examples, we can still achieve a compression rate of over 50%. And in terms of the efficiency of the algorithm, when compare the time to synthesize each subspec versus the time to complete the original synthesis task. So as you can see, for 80% of the request, this actually can be done in the time that is even shorter than the original synthesis task. And there's only few tasks that is really hard that takes more than 100 times of the original synthesis task. This shows that this algorithm itself is both very effective and very efficient. So to summarize my talk, we claim that the program synthesizers are becoming increasingly sophisticated, and to understand the implementation is taking more and more effort. So to handle this problem, we introduced the concept of subspecification to help explain the synthesizer's output. We also conduct a user study to demonstrate the usefulness of the subspec, and we developed a design algorithm to synthesize them, and we have also developed a lot of associated theory in the paper. Lastly, we implement our algorithm in the tool called S3. The artifact is available in this link or in this QR code if you're interested. And thank you very much. This is the end of my talk.
Oh, hello. Oh, really cool work. Is this limited to Cycus?
Sorry, are you asking that is it limited to Cycus?
Yeah.
No, actually, this concept can work for any program synthesis problem. And even in this paper, we have two domains. One is Cycus, another one is stream coder, which is completely different. In stream coder, is actually synthesizing lambda formulas using I/O examples.
And in that case, what are the subspecifications? What do they look like?
So for the stream coder, actually, for most of the cases, is still a pair of input-output, but sometimes it is not necessary. For example, it can be operator. For example, the first of this list must be 3, but it doesn't put any constraint for the remaining of the list. Something like this. It's not necessarily just the input-output constraint.
Yeah. My last question is, when you compress the specifications to be simpler, how do you tell the synthesizers that you want a simpler one? Do you just give a smaller grammar?
Yeah, or no, we're asking the synthesizer to synthesize a smaller program that is smaller specification that is equivalent to the original one.
So in the talk, you have shown like a specification from a competition, and that one looks pretty much more complicated than the implementation itself. So I'm just wondering, what is the point? Because for such specification is human unreadable, and I guess maybe that's the point. Also, you want to learn like some of the maybe more specific sub-specifications so that people can understand maybe part of the program well. So do you have any comments on that?
Yeah, I think you're asking a very good question over here. That indeed is a problem. That indeed is a very artificial examples, and we use them as a demonstration to see that this concept itself can be applied to different fields, but I agree that in reality you won't be likely to encounter specification like that. But you can see even with that, our simplification algorithm actually works very well, and we can somehow find the essence of the specification itself.
Yeah, I mean, especially when the synthesized program is getting complicated, and they will handle maybe different cases of specification, so that you can understand, like, split it into different parts.
Yes, that's true. I mean, because for the demonstration, we think that their simpler program might be easier to understand. I mean, we have some example that is rather complicated, but it might take too much space or too much time to explain.
Okay, thanks for your answer.
Thank you very much.
Okay, I have another couple of questions for you. I was really excited to see a user study here. So it's really neat. So I saw you had a bar chart showing comparing the result of your comparing results with subspecifications to results without subspecifications, and you said there was a significant difference, but I didn't see a hypothesis test. Did you do a hypothesis test?
I don't think we did.
Okay. So then we can't actually conclude that there's a significant difference, right? Unless we do the statistics.
Yes, that's true. Okay, sorry, could you repeat your question again? I didn't really catch it.
Yeah, so you argue that there's a significant difference between the two conditions, but I didn't see a hypothesis test that would actually show that statistically.
Oh, okay. I agree that might be a better approach, and maybe we should be more careful about that in our future work about the research user study.
Yeah, because that's important because you know you could make the same argument with n equals 1. Look, we compared the medians, and the medians were very different, right? But you actually have to look at the variance and the numbers and figure out, right? Okay. The other question I have for you is about the analysis of the qualitative data. So some of the questions that you asked the participants were sort of qualitative. If you go back to the slide with the questions, can you do this, and how would you? You had a few examples of questions a few slides back.
Oh.
I'm wondering how you analyze that data. So you're scoring the results to see. Yeah. So why, like the comprehension, the why question? How did you score the results of the why question?
So we have some certain. It's like you're grading the students' answers to a question. Like we have a certain point that is there's certain key part of the function that, if, for example, this function is calculating the maximum of the list, and then for example, a sorting function is you're getting the ith element at a time. For example, you get the smallest one, the second smallest one, the third smallest one. You need to capture the one or two of this crucial point. And for each of these problems, we design the crucial point. And if they hit the point, we give them a score. We are actually very mercy in grading. But still, I mean, without the subset, also they're just answering something that's completely irrelevant.
Sure. Okay. Neat. Thank you very much. Okay, let's have one more round of applause for our speaker.